Hello everyone, and welcome back to this tutorial series on the theory of computation. In this video, we'll be tying the knot on our discussion of NFAs and the conversion algorithm of NFAs to DFAs by discussing a very important theorem which results in the discussion of the conversion algorithm. So what this theorem states is something that I was trying to sort of give an intuition behind at the very beginning of the NFA tutorial videos. And it states that the set of all languages accepted by NFAs is exactly the same. So is exactly the same as the set of all languages accepted by DFAs. So if you think of the set of languages accepted by DFAs as just some blob, so each of these points are actually languages, right? So each element of LDFA is a language. So perhaps this language is, I don't know, the set of strings that have even length and that only have A's, right? So that could be one of the languages in LDFA, okay? Then there is a direct correspondence between the languages in LDFA, so the languages accepted by DFAs, and the languages accepted by NFAs. So this means that the sets are actually exactly the same, so they coincide. So this language here also exists in this language here, okay? And this language here that's accepted by NFAs also exists in this family of languages here, right? So these are family of languages. I might have misspoke there. These are family of languages, and any language that you can find here, you can also find here and vice versa, okay? And so why is this true? Well, the first sort of direction, right? So this is actually a subset inclusion proof, right? So what we're claiming is that these two family of languages are the same. And so to show this, you need to show that any DFA, any language accepted by a DFA, is also accepted by an NFA, and any language accepted by an NFA is also accepted by a DFA. And so at the very beginning of the tutorial series, I said how this direction was actually quite trivial. And the reason why this is trivial, okay, is because a DFA is actually an NFA that just doesn't use the non-determinism. So it just doesn't use the non-determinism of NFAs. So put it another way, if I have a DFA, let's say M, represented by the 5 tuple, okay, then it has a corresponding NFA N, where the tuple is almost exactly the same. So it has the same set of states, the same initial state, the same set of final states, of course the same alphabet. The only slight difference is the transition function. And the only difference in the transition function is that if you give it a state and some letter sigma, then it's going to give you only one and exactly one choice. So that's going to be represented as a set of a single transition, right? A set of a single next state. And that next state is going to be the one from the DFA, right? So just to highlight this, this is the transition function in the NFA. This is the transition function in the DFA, okay? So if you just say that the NFA has exactly one choice on all of its transitions, then this DFA automatically becomes an NFA, okay? And so that's why this direction is actually quite trivial, because if you take the language accepted by a DFA, right? So you take that DFA, you perform this very easy conversion, and so now you have a language that's accepted by an NFA. So that's why this part of the inclusion isn't that hard. The other part requires the conversion algorithm, right? So this required us to create the conversion algorithm. So the one thing that I omitted in the conversion algorithm was actually a proof of correctness, which arguably is the most important part of an algorithm. Okay, so in a proof of correctness, you essentially prove that your algorithm does what you state that it does. Okay, and so I'm going to omit it, but I'm going to give you the high-level idea, right? So the proof of correctness would go something like, I'm claiming I have some algorithm A, which takes an NFA N and converts it to a DFA M such that L of M is equal to L of N, right? So there's two parts to the claim of the algorithm, of what it does. The first thing is that it does a conversion, right? And then the other thing is that the conversion follows a certain property, right? It preserves something, okay? Well, certainly this is true, right? It's by sort of inspecting how the algorithm works, you can see that you're never going to introduce non-determinism, right? So this part would be relatively easy to argue, right? You just have to argue that non-determinism is completely removed, right? Completely removed. Okay. The less trivial part would be showing that the language accepted by the NFA is exactly the same as the language accepted by the DFA, and showing this formally. So I can give you maybe a high-level idea of what a proof of correctness for that would look like, right? So you have this NFA N, and you have this DFA M. So you're trying to show this. Because this is a set equality, you can again do this by double subset inclusion, right? So you argue first, you can argue first that if a string, actually I think the way that this would work logically is you'd probably first start with this, and then you'd go with this, right? So this is what you actually started with. This was your input to algorithm A, right? Did I give this algorithm a name? Yes, so this is algorithm A, that's the conversion algorithm. And so this is the input to algorithm A, M is the output of A, okay? And so what you want to do here in this part of the proof is you want to say for any string W in L of M, L of N, right? A string being an L of N implies that N accepts W, which implies that there exists a walk in N that starts at Q0 and ends in a final state. So there exists a walk W, of course. So the walk has to be labeled W, right? So you have to read the whole string. And this, of course, means that formally, this means that for the extended transition function of the NFA, if you start at Q0 and you read W, if you intersect that with F, you get at least one final state. Okay? And so you start by taking a string in L of N, and then what you want to do, right, you want to show, right, so you want to show that W is also an element, right? That is, in the DFA, when you give it the string W, it goes to a final state, right? So in the DFA, when you start at Q0 and you read W, it goes to a final state of your DFA, okay? And the whole idea behind the argument is that this is what your conversion algorithm was trying to do, right? So your conversion algorithm was taking all the possible choices and making them explicit, right? And so because in one of the possibilities, if your string does reach the final state, then that possibility has been encoded explicitly in the DFA. And so you will reach a final state because the existence, right, the existence in the NFA is explicitly materialized in the DFA. Okay, so that would be the general idea of the argument. I'm not going to write that down formally, right? But essentially, the conversion algorithm was made the existence of a walk explicit in the DFA. So explicit, I mean that it's listed all of the possible branchings, right? So if you remember in the NFA, what we also said is if you look at an NFA and you try to determine where it's going, maybe you have the string A, B, B. Maybe you could read the A, go to Q1, read the B, go back to Q1, and then read another B and go to Q2. Or maybe what you could also do is read the A, go to Q1, then directly go to Q2, and then go to Q3, let's say. And maybe this is a final state. And so what the conversion algorithm does is that it makes the choice explicit. So in making a choice between Q1 reading a B going back to Q1 and Q1 reading a B going back to Q2, you make this choice explicit in the DFA by saying if you read a B, you either go to Q1 or to Q2. So that means that you've sort of embedded one of the paths, one of the walks that goes to the final state within the choices. And so that's the general idea behind the correctness argument, okay? So the same would kind of hold, it would be the same type of argument, really, the same kind of logic, just kind of arguing in the reverse direction when starting from LM and going to LM, right? So this would be sort of the same kind of argument, but in the, say, opposite direction. So the only caveat you might be thinking of is with the empty string, right? So that's maybe the only caveat you might be seeing. Empty string, right? So you remember what I said was that if your NFA accepted the empty string and the initial state, so if this guy was not a final state in the DFA, you had to make this state a final state in the DFA, right? So this state should be made an accept state in the DFA. Of course, if it isn't already. If the machine, so if the NFA actually accepts the empty string, okay? And so you might be thinking, okay, well, doesn't this introduce the potential of false negatives or false positives? Could this not introduce false negatives or false positives? Well, my answer to that question and the proof of correctness would say no, because what would it mean? You have to think about what would it mean in your NFA for it to accept the empty string, but for the initial state not to be an accept state. So what that would mean, right, that would mean that the accept state in the NFA, right, is not an accept state, right? Sorry, the start state in the NFA, right? So if this is in the NFA, Q0 is not in F. Because if it was, right, because otherwise then Q0, like the set containing Q0 in the DFA would already be an accept state, and so you wouldn't have to go through this step, right? So if Q0 is not in F, okay, so that means that this in the DFA is not an accept state, right? But then if in the NFA, the empty string is accepted, what that means is that from the initial state, there's a sequence of only empty strings that allows you to reach a final state, right? So that means that with a free transition, with a lambda transition, there's a path that gets you to the final state, right? So if this happens, right, then lambda is accepted by the NFA, right? And at that point in the conversion algorithm, you should make the start state in your DFA a final state as well, even though it's not a final state in Q0. And so this doesn't introduce false positives, right? This doesn't introduce false positives because if there's something like a self loop here, right, then you could self loop all you want here, right? And then you could use this lambda transition to get to the final state. So that means that any number of A's could be followed by, let's say, 3 empty strings and could then reach the accept state. And so that means that if in the conversion algorithm you get Q0, right, so this is in the NFA. If in the converted DFA you get something like an A, right, and this isn't an accept state, but then because of this rule, right, because of this rule, you do make this an accept state. This additional, like these additional A's that are actually being accepted are not false positives. They actually should have been accepted because they can reach the final state. Okay? And you certainly don't introduce any false negatives because you're just adding final states, right? Okay, excellent. And so that's kind of just a small note about the caveat about the empty string, but in general, this is like the high level paintbrush strokes for proving the proof of correctness, for proving the correctness of the conversion algorithm. Okay, so supposing then that we believe that these two set inclusions are true, then we have an equality of the family of languages accepted by DFAs and NFAs. And so, as a corollary, what that means is that a language is regular if and only if there is an FA, which is either a DFA or an NFA that accepts it. Why? Right? So why? Because remember, by definition, L is regular if there exists a DFA M such that L of m is equal to L. But now, because we know that the family of languages accepted by DFAs is exactly the same by NFAs, this language here also has a corresponding language in the languages accepted by the NFA, by an NFA. So if we can create an NFA that accepts the language L, right, then we can convert it to the equivalent DFA, and then we'll have a DFA that accepts L. But because we said that NFAs are much more convenient to write, we can actually skip the conversion procedure and just say, because I have an NFA, and I know that NFAs are exactly equivalent in power to DFAs, then because I have this NFA that I've created that accepts the language, this means that the language that I've been asked to create an NFA for is regular, okay? And so what this allows us to do is that now, to prove that the language is regular, we can either create a DFA or an NFA. And so in this exercise, where we're asked to prove that the language XWX is regular, okay, because we've already created an NFA N such that the language accepted by N, if I label this L, is equal to L, this already proves that L is regular. Okay, and so we don't have to do any extra work of converting the NFA that we already had to a DFA. We can just use the fact that we have an NFA that accepts this language to prove that it's regular. And this is actually quite nice, right? Because like I said, sometimes building DFAs can be very tedious, whereas the equivalent NFA could be quite simple and quite elegant. Okay, excellent. And so this concludes our discussion of the equivalence between NFAs and DFAs.